The main thing we're trying to find are pairs of stars that orbit one another that are so close that one day they might collide or transfer mass and then potentially blow up as what's called a Type 1a supernova. Type 1a supernovae are some of the brightest objects we can see in the universe, and they all basically blow up with the same luminosity, the same overall brightness, such that if we see one blow up in the sky and we see how bright it looks to us, we know how far away it is. So they're sort of like rulers spread out through the universe, and they help us make measurements of the most distant objects in the universe. So we're trying to sift through thousands and thousands of stars to look for signatures of binaries that we care about. And traditionally from the ground, you might have to stare at a single star for 3, 4, 5 hours before you know whether it's interesting. That's just not practical for us. It would take decades. But if you go to space and you know in advance which targets are more likely to be interesting targets or variables, then you can save an awful lot of time. We've developed a method to kind of find strong candidates for variable stars using data from the European Space Agency satellite called Gaia. So Gaia observed millions of stars in the sky, and for each star it measured its brightness with an error bar, like how precise it knew the brightness. Well, it turns out if you have two stars that are perfectly identical, except one is a variable, it changes its brightness ever so slightly, and one is not, Gaia would have measured a bigger uncertainty for the brightness of the variable star. So by looking at something as boring as error bars, we've been able to sift out the stars that are most interesting. So before we had 5,000, 6,000 targets we wanted to look at, it would take way too long. With Gaia, we can say, out of those 5,000 or 6,000, there are 400 or 500 that have error bars that look way too big. There's something up with those stars. So we fed those stars to NASA and asked them to observe those objects with their TESS spacecraft. And it turns out about 95% of the stars we thought were interesting variables, in fact, are. So it saves a lot of time.
So tell me about the TESS spacecraft. What does that do?
TESS was originally designed to stare at a series of stars and monitor their brightnesses to look for planets blocking light from their background stars. TESS is generating light curves, brightness measurements for thousands of objects, so we can just pull those light curves down from the satellite, analyze them, and then search for the binaries that we care about. Binary star systems that are so close together, they orbit once every couple of hours, right? Earth takes a year to orbit the sun once completely. I'm talking about two stars that orbit one another once every few hours at speeds that are tremendous, hundreds of miles per second. So for one of these pairs of stars, we found that they're so close together, one will transfer mass to the other one, and that star happens to be what's called a white dwarf. And for white dwarfs, if you add just enough mass, that thing can explode as a Type 1a supernova. And we found one system in our galaxy, in our backyard, that will do that a few million years from now.
I'm sure NASA was excited about this.
Oh yeah, I mean, it's a great, efficient way to use their satellite. It's ancillary results from what they were expecting to get. For these supernovae, we need to know exactly how bright they are when they blow up. And until recently, we've only ever caught these supernovae after they've exploded. No one has ever found the binary star system that will generate these before they explode. And that's what we have found recently with this TESS project. So right now we see the two stars are safely orbiting one another, and from modeling the system, we can tell how long it will be before they mass transfer and roughly how long it will be before they blow up. So by studying that system now, we have a much better idea of what the explosion will be.